You're sitting on a moving train, staring out the window. Another train pulls alongside, moving in the same direction. For a moment, you can't tell which train is really moving. Welcome to the strange, mind-bending world of relative motion. Today, we're going to explore how motion depends entirely on your point of view. We'll see why there's no such thing as absolute motion. We'll learn how to calculate velocities in different reference frames, and we'll uncover a profound truth. While velocity depends on your frame, all inertial observers agree on acceleration. Our goal is clear: to describe reference frames and relative motion, to understand how the same event can look completely different depending on who's watching. So, what exactly is a reference frame? It's simply your chosen coordinate system for describing motion. It sets your origin, defines which directions are positive and negative, and, most importantly, determines what you consider to be at rest. When you say, the car is moving at 60 miles per hour, you're making a hidden assumption that Earth is your reference frame. But if you were in a helicopter flying alongside that car, the car might look nearly stationary. Same car, same moment, two completely different descriptions of motion. And that choice changes everything. Think of someone walking on a moving airport walkway. From the ground frame, their velocity is the sum of their walking speed plus the walkway's speed. From the walkway frame, they're just walking normally. From their own frame, they're standing still while the world slides past. 3 frames, 3 different stories, all describing the same reality. Now, let's bring in the math. Relative motion is all about vector addition and subtraction. The velocity you observe equals the object's velocity minus the velocity of your frame. In symbols, V observed equals V object minus V observer. Take an example. A boat moves north at 20 meters per second relative to the water. The water itself flows east at 5 meters per second. What's the boat's velocity relative to the shore? We add the vector velocities. Since the directions are perpendicular, we use the Pythagorean theorem. The magnitude is the square root of 20 squared plus 5 squared. That's square root of 425, which equals 20.6 meters per second. The direction? Tangent of 20 over 5, giving about 76 degrees north of east. Same boat, same path, but the description depends entirely on the chosen frame. For motion in one dimension, things simplify. Imagine 2 cars on a highway driving toward each other. Car A moves east at 30 meters per second. Car B moves west at 20 meters per second. From car A's perspective, car B approaches at 50 meters per second. From car B's perspective, car A does the same. From the ground's perspective, their relative approach speed is also 50 meters per second. Different frames, same outcome. Now, let's return to the trains. Train A moves east at 40 meters per second. Train B moves east at 35 meters per second. From train A's frame, train B drifts west at 5 meters per second. From train B's frame, train A drifts east at 5 meters per second. That's why passengers see the other trains sliding slowly backward, even though both are moving forward. Here's where things get profound. Velocity depends on your frame, but acceleration does not. In fact, all inertial frames that are not accelerating, measure the same acceleration for an object. If you're in a car moving at constant speed, you're in an inertial frame. If the car speeds up or turns, you're not. This invariance of acceleration is one of the bedrock principles of physics, and it has real-world consequences. Air traffic controllers account for both wind velocity and plane velocity. Sailors must factor in the current when navigating. Spacecraft engineers calculate motion relative to Earth, the Moon, and their target planet. Even your GPS chip solves relative motion equations non-stop, comparing satellite signals and Earth's frame to pinpoint your position. Relative motion isn't just theory, it's technology, safety, and exploration. So, let's recap. Reference frames define coordinate systems and decide what's at rest. The same motion can look completely different depending on the observer. Velocities combine through vector addition and subtraction. And acceleration in any inertial frame stays the same. In our next video, we'll go deeper into vectors and two-dimensional motion. We'll break motion into components and tackle projectile problems, because the real world doesn't move in straight lines. For now, remember this: motion is always relative to something. Choose your reference frame wisely. The physics stays the same, but your perspective changes.